So two announcements before we start. Do you get any feedback or it's only me? It's okay? Okay, so one, I don't want to forget, in the next 3 meetings, just after class, there is a machine learning lecture, faculty interview. So today, Tuesday, next Tuesday and next Thursday, there's going to be faculty candidates. All of them are machine learning people. So if you have time, will be good talks. So I highly recommend that you stay. There's a fourth one that is on Monday at 10 in town 337. So there's going to be 4 lectures that could be of interest to many of them. So that's one. 2, there have been some requests to extend the current problem set to beyond Saturday, which is due, and we're going to extend it to Monday night. So I knew that you have nothing else to do this weekend, so now you can do that. So, okay, so we'll announce it a little bit later. Okay, so questions? Any questions? Anything? Other concerns? Yes. So today is someone that is doing somewhere between learning theory and algorithmic game theory. Tuesday is machine learning for natural language processing. Thursday is machine learning for vision, adaptation in vision, and so on. Okay, so where are we? So we started talking about Bayes nets, basically a representation of a probability distribution. So the example that we basically ended up with, we have variables. Each one of them is a Boolean variables, and we gave it some meaning. Once we have these 6 variables, there are many, many probability distributions that can define on these variables. And BaseNet is a language, if you want, to represent a family of probability distributions over this. And specifically, there is a graphical convention that says that if we take these variables, these are the meanings of some of the variables here. They're all Boolean variables. And we add these arrows with this directed acyclic graph, we actually defined a specific probability distribution, or in fact, a family of probability distribution. We still need to give you some collections of numbers to completely define it. But this defines what are the numbers that I need to give you to define this concretely. Yeah.
Quick question. So in this case, we only have like a Bernoulli for each one, but you could potentially have any distribution. So burglary, yes or no, we could have like a Poisson distribution that comes up with, I don't know, like a number of how many items they're stealing from your house, and then basically.
So in principle, yes. What this defines is what are the conditional probability tables that I need to give you. I need to define here what is the probability of John calls given alarm. What is this probability distribution is up to you as the person that defines the probability distribution, or maybe if you want to learn from data. I'm actually going to give you specific numbers here. But you could also say, you know what, this is a Poisson distribution with these parameters, or you can say this is a Bernoulli with this parameter. So all this defines is the structure and what are the conditional probabilities needed in order to do it. So now I can do one of 2 things. I can just give you these numbers exactly, or I can tell you something about these numbers without concretely give it to you. And you'll see both cases. So these are small cases, really toy problems. So I'm going to give you the probability distribution concretely. But in all cases, the graph determines the independence assumptions. right? So how you treat this arrow, or how you treat this, here you want to know probability of alarm given earthquake and burglary. This is well defined from the convention. Which probability distribution sits here and defines P of alarm given earthquake and burglary, it's up to you. Okay, so now what we said is that given that I have these 6 variables, originally I could have asked how many parameters in general we would have on a probability distribution over 6 variables. And we agree that this could range from 1 parameter, the probability of all variable is 6, independent, to 6 parameters. These are independent variables. The probability of earthquake being 1 is 0.5, the probability of burglary being 1 is 0.3, and so on, 6 numbers, up to 2 to the 6, which is everything is possible, or 2 to the 6 minus 1. But here, because we defined this structure, we restricted it to be defined using this conditional probability table, and then we counted how many, and we got, I don't know what, like 30-some numbers that we'll define. So we went down from 2 to the 6, which is 64, to 20-something or 30-something parameters. Okay, so basically, one important thing for you here is to really understand this language. And understanding this language essentially implies that there is a theorem here that says, how do we write the joint probability distribution over these 6 variables? And I've written it here. So P of E, B, A, R, M, J can be written using essentially Bayes' rule plus these assumptions as this. P of E, P of B, P of R given E, P of A given B, and where am I? R given E, M given A, which is this, J given A, and A given E and B. Basically, the product of all the probability of nodes given their parents. Okay, so now, in practice, what do we want to do? Really, we have 2 computational problems. We want to learn this probability distribution, which in this case, or in general, implies learning the structure. Here I gave you the structure. I showed you what are the edges. In general, you want to learn it, and once you have the structure, you want to learn the parameters. Once you have it, you have the inference problem. Or in fact, it's not once you have it. Inference is part of the learning, as we'll see a little bit later today. And there are 2 key inference questions that you may want to ask. One of them is, give me an event. An event means an assignment to some of the variables. Could be a conditional event. Could be that I observe something. I observe that A is 1 and B is 0. And now I want to know what's the probability of J and M being 1. So that's one event. And the second, and that's one inference task. And the second one is you make some observation. So you observe that A is 0 and B is 1. And you want to know, give me the most likely assignment to some other variables that I care about. These 2 inference problems have names. The name of the second one has changed with time. It used to be called MPE. I'm writing it here. For some reason that I actually don't get, this has changed to be called MAP in the more recent literature. So don't be confused if you read a more classical or better literature on this, but anyhow, these are the problems. And both of these are hard problems computationally in the general case, and therefore we're not going to talk about them a lot. I'm going to give some hints to what are the approaches, But most of the time today, we're going to spend on a restricted case of Bayes nets, which are in the form of trees. And the reason is that it still has a lot of the nice properties of Bayes nets, and it's much simpler, and we can give an interesting and a nice algorithm to learn these. So most of the principles that I want you to understand, we can still understand in the context of trees. So what does it mean that it's a tree? That when I write this joint probability distribution, P of, in this case, I drew it as P of y, comma, x1, x2 up to xn, we can write it again as P of y times the product of P of xi given its parents, but the parents, there's only one parent because it's a tree. This is the simplification, turns out to be a very significant simplification. Okay, so what are the problems? Again, we have an inference problem, which is given the tree with all the associated probability, compute the probability of some events. Question?
Yeah, with the independence assumption, can we also say that B is independent of W given Y?
Say again, what are the names?
B is independent of W given Y. Does that also hold?
Yes, yes. So given the parent,
Even if it's not a direct parent?
yeah, because, and we're going to see it in a second, in fact, yeah. V is independent of W given Y. Yeah. V is also independent of Y given U. Right? V is independent of Y given U. Okay? Given U, you don't care about anything else. V is determined. So think about the independence assumptions that we have. V is independent of anything else given U, because U is the only parent of V. Okay, in particular, V is independent of W given U, V is independent of Y given U. Okay, so go back to the definition of what we mean. So really the parents determine what's happening. No, okay, so if you're talking about someone outside the subtree like W, it's also true that given Y, W and V are independent. You can just write it down and see it. Assume that everything is independent of V given U, and you can derive that W is independent of V given Y also. We're going to write something down. So basically, my goal in the next few minutes is to convince you that you know how to do inference on these trees. So I'm not going to give you a formal algorithm, but we're going to try a few cases and convince ourselves that we know how to compute it. So let's start by computing the probability of this event, the event x equal 1. Now, we don't know it ahead of time because it's not one of these numbers. I've given you, you know what are the numbers that define this probability distribution. It's P of y, and then let's assume everything is Boolean here. So 4 numbers on each of the edges, right? So the edge between z to x, I need to give you these numbers, P of x given z. In the Boolean case, it means P of x being 0 and 1 given z being 0 and 1. Same thing here, P of t given z, P of v given u, P of w given y, and all this. That's what I'm giving you. And now I'm asking you, how are we going to compute P of x being 1? So the only thing that you want to recall, if you haven't played with it, is marginalization and product rule. So in this case, I'm going to marginalize. Essentially, I'm going to climb up the tree. So first of all, I'm going to marginalize over z, which is going to give me that P of x being 1 is P of x being 1 given z being 1 times P of z being 1 plus P of x being 1 given z equals 0 times P of z being 0. You should know this. Now, I still don't know everything, right? So I know P of x given z, right? It's written, but I don't know P of Z. So I'm going to keep on climbing up the tree recursively. P of Z, again, can be computed by marginalizing over Y. So P of Z being 1 is P of Z being 1 given Y being 1 times P of Y being 1 plus P of Z being 1 given Y equals 0 times P of Y equals 0. And I can write the same thing for P of Z being 0, and we're done. So essentially, marginalization and climbing up the tree gave me this event. Questions? Okay, let's try another event. Just the important thing is for you to notice that what I've done is I started with an event and I've climbed up the tree so I can write it as a function of the given conditional probabilities, conditional probability tables, the CPTs. Okay, here is another event, P of X being 1 and Y being 0. Again, I don't know this. I have to compute it given the CPTs. And as before, P of X, it's equal to P of X being 1 given that Y is 0 times P that Y times the probability that Y is 0. And I don't know, I know P of Y being 0 because Y is the root. I do not know P of X given Y because they are not connected directly. So I need to climb up, I'm going to climb up the tree from X all the way to Y. In this case, there's only one node in the middle, so it's going to be easy. I'm going to do it by marginalizing over Z. So P of X given Y, I can write as summing over Z, P of X given Y and Z times P of Z given Y. Again, make sure that you're comfortable with this. And what happens now? So first of all, I'm going to simplify it a little bit. P of X given Y and Z, it's enough to write P of X given Z because X is independent of Y given Z. Again, there is a path here, Y, Z, X. X given Z is independent of Y. And therefore, this expression I can write this way. And it so happened that I know this number already. P of X given Z is given as part of the definition of the Bayes net. P of Z given Y is also given as part of the definition because there is an edge here. So basically, I know how to compute this probability distribution also. Again, I managed to write it in terms of the CPTs. The only other thing I still need to convince you of is what happens if you define an event that involves variables that do not have a direct path. So for example, I'm going to look at X and U. So the question that you asked before, X and U do not have a direct path, and let's see what do I do. Now, what's going to help me here is the fact that it's a tree. They don't have a direct path, but there is one node, for sure, that is a parent, directly or indirectly, of both of them. So I'm going to climb up to this one. So if I want to compute P of X given U, P of X and U, P of X being 1 in this case, and U being 0, I can write it as P of X given U times P of U. And I'm going to find a node that is a joint parent of both of them. We always have one. It's a tree. And therefore, I can write it P of X given U as marginalizing over Y, P of X given U and Y times P of Y given U. We've already done this before. And just like before, so I'm copying this, and here I'm saying, given Y, This is what we started the response to your question. Given y, x is independent of u. So I can just, instead of writing this, I can write this. And now the same thing. So now I've written it in terms of things that we already know what to do with. We already computed p of x given y in the previous slide. We already computed, well, we almost computed p of y given u. What else is missing? How do I compute p of y given u? I'll have to use Bayes' rule, right? Because y is above u in my network. So I'll have to write it as p of u given y, which I know, times p of y divided by p of u, and I know how to compute this. Okay? So basically, my goal here was, without writing it in any formal way, to convince you that we know how to evaluate all the probabilities you care about. You know how to do inference over Bayesian trees. Okay, so I basically showed it by example. Not necessarily the best algorithm. There are more efficient algorithms that, in fact, will be logarithmic in the number of nodes with a lot of caching and stuff like this. But basically, it's an easy problem. Okay, so now that we have that, again, I want to make the comment that this is a simple case. We're lucky. In the general case, it's not going to be so easy. And the key reason is that when you have a graph, a DAG rather than a tree, when you're looking at two variables, there could be multiple paths that connect them. And you have to take this into account if you want to compute the probabilities. So you'll have to go multiple ways, and this could be complicated. I'm not going to talk about this problem. I just want to give a few hints. There are really two ways to think about inference in the general case. One of them is exact inference. There are multiple algorithms. All of them kind of resort to what is called variable elimination. And I'm going to give just a hint. So what is variable elimination? This is what I want to compute. I want to compute the joint p of x up to xn, say, and I know that I can write it as the product of p of xi given the parents. What I'm going to do is I'm going to do a marginalization. So if I want to compute p of x1, I'm going to take this joint and marginalize over all the other variables, all the n minus 1 variables. So I'm going to write p of x given 1, p of x1 as p of x 1 up to n, marginalizing over 2x2 to xn. Now notice that I can break this down using this way. And therefore, I can order the sum any way I want. Specifically, I order it here in increasing order. Now, this is going to be a tough computation in the general case, right? Because I'll have to instantiate 2 to the n minus 1 times. The only thing that variable elimination does is, in fact, think about it as a data structure or as an organized programmer, where what we do is we guess an order. Some orders might be better than others, and there's no recipes for this. You just need to hope that the order that you've chosen is good. 2, you're caching stuff in between. So for example, I'm going to give you a simple example with this Bayes net. Now, this is a very simple Bayes net. In fact, it's a tree. Nevertheless, the idea of Bayesian of variable elimination will go through. So I want to compute P of C. What do I do? First of all, I'm going to write P of C as marginalization over A and B. Now, how do I write P of ABC? P of ABC for this Bayes net can be written as P of A, P of B given A, P of C given B. Okay? That's something that you should be comfortable with. So now the question is, can I evolve? Now think about it. Each one of these has 4 numbers, right? Really. So it's going to be a lot of numbers, large sums here. Okay? Now notice that P of C given B does not depend on A at all. So I can take it outside the A sum. So I can really write it this way. Inside I'm going to have P of sum over A of P of A times P of B given A. And only once I computed this, I'm going to sum over B P of C given B. I haven't done anything here. I just reordered it. I chose to single out A and put it inside. Now, what I mean when I said data structure, now you can observe that this sum here really is independent of A. It's a function of B, right? Because I summed already, I marginalized A away already in this component. So what I'm going to do is I'm going to compute it once, rather than many times if I look at it this way, and I'm not thinking about being efficient. I'm going to compute this one, cache it, and give it to this guy. So I'm going to denote this by FA of B. Notice it's independent of A. It's a function of the values of B. And just write it this way. That's the trick of variable elimination. Yes?
In the formula where with P of A, B, C, that multiplication of three things, should it be probability of C given B and A?
No, because, good question, why not?
Given B, we don't care about it.
Given B, C is independent of A. Okay?
Why?
Because that's the assumption of BaseNet. That's the convention here. If I drew an arrow A to B and B to C, what I'm saying is that given B, C is independent of A. Given the parent of C, C is independent of anything else, in particular of A. Okay? So before I drew it vertically, when I drew the tree, it's the same question that we had before when we talked about X is independent of Y given Z. Right? You agree it's the same thing? So that's a convention. So once I draw this, I tell you the joint probability P of A, B, C is defined is this. Okay, so basically what I said, I gave you the simplest possible example of what is variable elimination, and hopefully you can appreciate that I did nothing. All I did is just observe that if you do the computation in the right order and cache stuff, you can save a little bit of computation. In the limit, it's not going to help me. The problem is hard, it's going to stay hard, unless I'm lucky and I've chosen some order that makes it easy in this case. So in the notes, and I'm not going to go over it, I did another example of variable elimination for this graph, a little bit more complicated, same idea. So if you want to really understand what's happening, you can go over this. You don't have to. I just want you to know that this exists. And as I said, okay, that's the example. I'm going to run over it. The important thing for you to know, it's really not going to help. In the worst case, it's still intractable. As I said last time, the exact inference in BaseNet is Sharpie complete, Sharpie hard. For people that know, you know about NP complete. NP complete is equivalent to finding a satisfying assignment of a CNF, let's say 3 CNF. Sharpie complete is equivalent to counting the number of satisfying assignments of a CNF. So rather than finding a satisfying assignment, count how many satisfying assignments there are. This is a harder problem. We know that it's a harder problem. That's why exact inference in BaseNet is NP-hard. Still, it's an industry in the sense that you can find good packages. There are good algorithms. There's a lot of improvement that happened over the last 2 decades in this, and there's competitions. So if you really need to do this, you can find a package that does it. A lot of people, though, resort to approximate inference. There are multiple ways to do approximate inference. The most common one is something that is called Gibbs sampling. I'm not going to give the details on this also, but I'm going to give you some intuition. So what is the intuition? How can we approximately do inference here? A good way to think about it, I think, is look at this picture. Let's assume that, so your universe is this rectangle, and I'm asking you, what is the area of this weird shape in the middle that I denoted X? What is the area of this? Now, if the area was kind of regularly shaped, you'll have a formula to do it, right? If it's a polygon or something like this, there's a formula. But this X is kind of a weird shape. How would you find the area of X? Yeah?
Well, you're saying approximately I shrink the rectangle until it's, so say like the top is touching the very topmost part of X, and then I'll do the same until basically the farthest points on each side are touching the box, and then I'll just approximate it as the area.
Okay, so that's one solution. It will give you some approximation, not the best approximation there is, but will be an approximation. Another suggestion?
I'll draw grids and see how many grids.
Right, so grid is another way to go. Yes?
Just like throw darts at it, and just count the number of darts that land in the dark spot versus the white spot.
Yes, so darts, or I'm going to call it sampling. Let's assume you can sample points from the rectangle. And you know if a point fell inside X or not. So sample 1,000 points or draw 1,000 darts and count how many of them fell inside X. Let's say 613 fell inside X, then the area, an approximation for the area of X is 613 over 1,000. Now this is if you want to do the area. Now which means that this board is flat, right? Now assume that there is a probability distribution, which means it's not flat, it's kind of hilly. Same idea. If you sample from this probability distribution, you can count in a weighted way, right? Rather than just count the number of darts, give weights according to P of X. And this would give you an estimate. So that's the idea of Gibbs sampling. Now, the key difficulty, of course, is how do I sample from this probability distribution? And there are many, many, many ways to do it. And basically, the ideas have to do with some random walks in this rectangle where you count how many times you go into X and how many times you don't. And there's a lot of technical difficulties. So I'm not going to go into this. This is out of the scope of what we want to say. I have a few slides on this for people that are interested. And you can go from this to the literature. I just wanted to give you an idea. So, okay, so where are we? We talked about Bayes nets, we talked about inference in the general case, and we want to talk about learning. And again, I'm going to simplify our life and talk about learning in the case of tree-dependent distributions. Hopefully, we are convinced that this is simpler, but as we'll see, interesting enough. So what is our problem here? What is the learning problem? Here is one way to think about the learning problem. I'm going to give you data, tuples, n tuples, where n is the number of variables in this tree. I'm assuming, let's say, that these n tuples were sampled from this probability distribution. And the question is, okay, so first of all, you have to make sure that you understand what I mean by these n tuples were sampled from this probability distribution. Think about the generative process. How do I generate data according to this? I generate y according to P of y. Given the value of y, I'm going to generate now w based on P of w given y. I'm going to generate u based on P of u given y. z based on p of z given y and so on. Once I have z, I can generate x given p of x given z and p of t given z and so on. So that's how data is being generated. Now that it's been generated using this mechanism and you look at the data, the question for you, okay, so now reverse engineering it. Given the data, tell me what is the tree on what and what were the probabilities that I put there. Right? That's the learning problem. So we know what it means. We think about the generative model. And really what we want is to find the tree representation of this distribution. What does it mean that I want to find the tree representation? Yeah, but is there a tree that generates the data? Could be infinitely many trees that would have generated this data. So what is the principle that guides us these few weeks? Maximum likelihood. So there could be many trees, and we're going to try to find the most likely tree that could have generated this data. So if I give you a tree and the data, you should be able to tell me what's the likelihood of the tree given the data, or what's the likelihood of the data given this tree. Same thing given Bayes rules. So you will entertain multiple trees. You fix this data that I gave you, and you ask which of these trees is more likely given the data. That's the game that we're going to play. Okay, so we know what that means. That means among all the trees, find the most likely one given the data. So basically, that's what we are doing. We are computing P of t given the data, which is, Bayes' rule says P of d, the data given the tree, P of t divided by P of d. We will not care about P of d. We will care about P of t. But in most cases, we're going to, because of the argmax, this is going to disappear. Because we don't have any preferences, this will disappear. So really, we care about the probability of the data given the tree. And we know how to compute it, as we'll see in a second. Okay, so this is one way we thought about it. And as I said, I'm just repeating what I just said. We are assuming uniform distribution over the tree. So we really care about maximum likelihood. So we care about the probability of the data given the tree, which we know that we can write as argmax over all the data points. The probability given the tree of the data. This is my notation now. So what I mean here is the same thing that I meant here. For this tree, what is the probability of this data point? And I'm going to multiply over all data points because I'm assuming that these data points were sampled independently from this tree distribution. So in particular, now you understand why we talked about inference before we talk about learning. Because I should be able to compute, here is a tree, what is the probability of this data point? Which is the inference problem, right? Okay, so just to spell this out, it's the argmax of the product over all data points, P of xi given the parent of xi for this tree. Okay, that's what we are doing. Now, if you think about it, we've done this for naive Bayes. We found what you're doing with naive Bayes is essentially doing this. Think a little bit about this and see that that's what you're doing. And then let's take an example. So I'm going to give you some distributions. Here is one distribution. I have 4 variables. So this is a probability distribution over 4 variables. Here is another probability distribution over 4 variables. In fact, this is a family of probability distribution over 4 variables because I didn't give you the conditional probabilities yet. Now I did. If these were numbers, this is another probability distribution over 4 variables. Here is another one. So now I can ask you, you have 3 probability distribution. I can ask you, are these the same distribution? What does it mean for 2 trees, let's say, or for 2 representation of a probability to be the same probability distribution? Just a definitional thing. Make sure that we are thinking. What does it mean? So I show you each probability distribution could have many, many representations. Right? Here is one representation, that what I call here distribution 1 is a representation of probability distribution. I can probably write the same probability distribution otherwise. So I'm asking you whether these 3 represent the same probability distribution. And I just want to make sure that we understand what does it mean that 2 things are the same probability distribution. Yeah? Yes. For each event, these 2 things give the same probability distribution. So I'm asking this question for a reason that you'll understand at the end, and also when you do the last problem set. So another question I can ask is, given a sample, which of these 3 generated it? Or you could correct me, which of these distribution is more likely to have generated it. So let's do this. So here is data. I gave you data points, 3 data points, and the exercise is which is the target distribution? Which of these 3 is the target distribution? So we can just compute. Here is 1. Could this have generated these probabilities, this data? Why yes, why no? Yes?
No, because the first number 1011 has a probability of 0.
Yes. So the point 1011 has 0 support under probability distribution 1. This data set couldn't have been generated from this. The likelihood is 0. I can write it, right? So what is the likelihood that this table generated the data? P of t given d. I can write this down, and I get 0. Because of this data point that you identify, 1011. Okay? Okay, we eliminated one candidate. P of the data given the table is 0. Now we can work on this one. I need to give you the numbers to make this a probability distribution. Here are the numbers. Now make sure that you agree that these are the numbers that I should have given you to define this probability distribution exactly. And now that you have the numbers, you can compute. You can compute the likelihood of the 3 given this data. Okay? And that's what I did here. So I have to do it for each data point. So P of 1011 given this 3 is, remember, what is this 3? This 3 is defined as this distribution. So how do I write the probability of this point? It's P of x4 times P of x1 given x4, P of x2 given x4, P of x3 given x4. This is really a naive Bayes distribution, right? So you know that. So that's what I've written here. P of x4 being 1 because it's 1 here. P of x1 given x4, both of them are 1. P of x2 being 0, x4 being 1, because x2 is 0 and x4 is 1, and so on. I computed the probability for this data point. That's the probability that it was generated by this 3. And now I can do this for the other data points, and the product gives me the probability that this data was generated by the 3. Okay? I can do the same thing for the other data point. Again, the important thing for you to understand is that I've given you the right conditional probability to define this probability distribution, and that you know that if I want to compute P of 1, 0, 1, 1, I need to know P of x4 times P of x1 given x4 times P of x2 given x4 times P of x3 given x2. Okay? Once you agree with that, you got this right, then you can compute. And we get this number, and it so happened that distribution 2 is the most likely distribution to have produced this data. Okay, so what have we done so far? I gave you 3 probability distributions that are candidates. I gave you data, and you solved the learning problem. You told me which of these probability distributions is the most likely one to have generated the data. Is this the problem we want to solve? Or how do we want to generalize beyond this? Yeah? Suggestion?
How was the tree structure decided?
Say it again.
How was the tree structure, the candidates, how are they already given?
I chose it. I had some information and I knew that these are the 3 candidates. But why isn't that the whole problem we want to solve? Exactly for that reason, because why did you choose these 3? There are other trees. So if you want to go back to what we've done 2 weeks ago, we are now in the same situation we were when I gave you 2 points. One of them was a biased coin, and another one was a fair coin. Bias 0.7, 0.3, say, I think it was 0.6, 0.4 there, and a fair one. And I ask you, let's toss the coin a few times and see which one of these 2 is the more likely to have generated these tosses. Okay? And basically, the exercise that we've done with the 3 trees is completely equivalent to the exercise we've done with the 2 coins. Only different representation of the probability distribution. I want to make sure that you all get this level of abstraction here, because in your real life, what you're going to do is you're going to do the same thing with a different probability distribution that will be relevant to your application. But it's really the same game. And when we did it then, we said, okay, we understand the game. We can decide which of these 2 is more likely, but that's not the real problem. The real problem is, here's a coin. I don't know that there are only 2 options for the bias of the coin. There are infinitely many options. And we then solve the problem with the infinitely many options for P, the probability of head. And that's what we want to do now, right? So we want to generalize from the 3 trees to all trees. So we need a systematic way to search over the family of trees. That's the challenge that we have. Okay, so I want to say one other thing that, okay, in fact, why do we care about this? I hope all of you could answer this question. So what is the real goal? I mean, why do I want to be able to learn this probability distribution at all? Yes?
The whole point of naive Bayes is you learn the probability distribution so that you can, given future examples, you can classify them as coming from that distribution.
Yeah, so the goal is to be able to predict the new examples. That's it. That was the goal for naive Bayes. That was the goal for perceptron. That is the goal for this. I want to learn a model so that I can make predictions. Now, if I only have these 3 data points, I cannot make predictions. Because all I know is that the probability of 1011 is non-zero, the probability of 1001 is non-zero, and 0100 is non-zero. Maybe I know that it's a third for each, I don't know. But I cannot make predictions. In order to make predictions and new data points, I have to make assumptions. Where is this coming from? And these assumptions will allow me to make predictions on data points I've never seen before. That's the game. So for example, given the data points, I cannot tell you what is the probability of this middle point here, which is x1 is 1, x2 is 1. I don't know about 3 and 4. What is the probability of this? I don't know. Right? I have to make assumptions, learn a model, and today our model is a probabilistic tree. Now I can make prediction on any data point, on any event. Okay? So that has to be clear. I mean, the data itself is not sufficient. You have to make assumptions. Okay. So let's go back to the learning problem. And now we're going to solve the general learning problem. But before that, I want to generalize the problem a little bit. So before we said, given data, assume to be sampled from a tree-dependent distribution, find the most probable tree to have generated this data. It turns out that I can actually generalize this for the same price, same algorithm is going to do it. Given data, I don't know where it came from, find the best tree representation that could have generated it. So notice that these are two different problems. Here is perhaps a way to think about it. This is the space of all tree distributions. Okay? All the points there are tree distributions. Now, remember, not all distributions can be written as tree distributions. It's a specific set of independent assumptions. And the first question at the top left is the target distribution is there. Take some data, find it. The second problem says, well, there is a space of all distributions. It's a larger space. The probability distribution, the target one could be here. What I'm going to do is I'm going to find this red point, which is a tree distribution, because my algorithm will only be able to learn tree distributions. But it's the tree distribution that is the closest, under some definition of close, to the target one. Okay? So that's a more general setting. Again, if you want to go back to the beginning of the class, to the first part of the class, we talked at the beginning about, here is a hidden function, it's a conjunction. Learn it. Or, we later on said, here is a function. I don't know, I'm going to learn it using a linear function. I don't know that I can actually express this hidden function with a linear function. Nevertheless, I'm going to try. I'm going to have some empirical error, but I'm going to find the best linear function given the data that you've given me. So that's analogous to the game we were playing here. Questions? Okay, so let's not do it. This is what we've said before. The simple-minded algorithm is going to be to compute P of t, do this argmax, and then figure out a way to find the maximal one. What we're going to do is we're going to actually have a clever algorithm that doesn't need to do search. It's going to find this, okay, where's this nice picture that I had? What's happening? Oh, this nice picture. We're going to figure out how to find this red point here. Now, in order to find this red point, as I said, we need a notion of distance between distributions. So that's the first thing that I'm going to introduce. Now, if you think about it, you already have a notion of distance between distribution. What is a distribution? It's just a function that ranges between 0 and 1. So you can take your domain, you can plot a function that sums to 1, and then you can plot another function that sums to 1, and you can find somehow the distance between them. For every point, I don't know, look at the difference between y of this point, sum it up, or look at the absolute value or the square, or do something that is a distance between two functions. I'm going to suggest a different function that is called KL divergence. It's an important notion. It's an entropy-based measure, and it's defined this way. The distance between probability distribution P and T is sum over all x's. It's a discrete space. Sum over all x's, P of x times log P of x divided by T of x. So it's really not a distance function, but because it's not symmetric even. But we're going to call it a distance between probability distribution. The reason we like this probability distribution will be clear from the details of the proof that I'm not going to go into. But in general, this is a commonly used way to measure distance between distributions, so it's good to know. So that's one component that you need to know for this. The second component that you need to know is I'm going to learn a tree. So we have to be able to make a decision. I have two nodes. The nodes are known to me. How do I decide whether I put an edge between x and y or not? So basically, I'm going to use a specific way to measure how related x and y are, and use this to determine whether I want to put an edge between x and y. And the measure that I'm going to use to decide how related x and y are is mutual information. So this is how I'm going to define it. So basically the information of x given y, if you want, it's called I of xi, and I'm summing over all pairs, all values that x and y take, P of xy, the joint probability distribution P of xy, times log P of xy divided by P of x, P of y. So you should be familiar with these things. You know, P of xy divided by P of x, P of y determines the dependence between them, right? So if x and y are independent, this is going to be 1. In general, it's not going to be 1, but this is going to allow us to measure how much it is, and then I'm going to average over all possible values, weighted over all possible values of x and y. Okay, so now I have these two formulas. Again, this one to allow me to measure the dependence, if you want, between x and y, and the previous one just to measure distance between distribution, and now I can give an algorithm. So here's the algorithm. The algorithm is given m independent measurements from the probability distribution. First of all, for each variable, I'm going to estimate P of x. We know how to do this, right? Let's assume that we're assuming Bernoulli, so we're counting. For each pair of variables, x, y, I'm going to estimate P of xy. Again, you know how to do this. One thing to remember here is that it's n square numbers. What does that mean? So think about naive Bayes. How many numbers do you need to estimate in order to learn naive Bayes? If you have n variables, how many numbers do you have to estimate?
How many labels are there?
Let's assume that all the variables are Boolean variables. How many numbers? You're coding it now. You should remember. N variables. How many? N plus 1 times v. Okay, let's say everything is Boolean here. So something like 2n, right? Maybe 2n plus 2. Linear in n. Okay, that's the important thing here. Whether it's Boolean or has k values, it's going to be linear in n, right? Because basically you need the prior, and then P of xi given y for each I. So n variables, linear in n numbers. What happens here? Quadratic. Because I have to look at all pairs in order to decide, do I put an edge there or not? I didn't have to make this decision for the naive Bayes. That means that if you have, how many features do you have in your problem? In your homework problem? What's the dimensionality? Give me a number. 180,000, 10 to the 6 or so, right? How many numbers will you need here? 10 to the 12, large number, okay? If you want to think about your numbers as 10 to the 5 even, just 100,000, 10 to the 10. Storage could be an issue, okay? Just to remember that. So whenever you go beyond kind of these linear structures, you have to start thinking, because could be large. Even this simple algorithm could be large. Anyhow, that's what we do. We have O of n square numbers. So that basically means that when you think about things, you don't always need to think about time. You often need to think about memory. Memory is cheap, but still, when you need a lot, you have to think. Okay. So now that I have these pairs, for each pair, I can compute the mutual information, right? I got P of X, I got P of Y, I got P of XY. I can compute the mutual information, which I defined before. What I'm going to do now, I'm going to build a complete undirected graph with all the variables as vertices. A complete undirected graph. So I'm going to connect everything. And now I'm going to prune these edges. So if I of xi is, I'm considering this as the weight of the edge xy, what I'm going to do is I'm going to build a maximum weighted spanning tree on this graph. So this is going to be my way of taking the complete graph, getting it into a tree. How do I do this? Hopefully you've all seen a spanning tree algorithm, so I'm just going to remind you, how do I find a spanning tree? My goal is to find a subset of the edges in the complete graph that form a tree, which means I want to include all the vertices, but I want the total weight of the edges to be maximized. So the way I do it is in a greedy way. I'm sorting the weights. I'm starting greedily with the highest weight, highest edge, or heaviest edge if you want. And then I'm adding the next largest as long as I didn't create a loop. If I do create a loop, I'm going to discard this weight and move to the next one. And I'm going to keep on going. Not difficult to see that this algorithm will create a tree. It's a spanning tree in the sense that it touches all the vertices. And it's going to be the maximum weighted spanning tree. And the complexity of this is n squared log n because of the sorting, basically. You knew that it's going to be n squared because you touch n squared things. Because of the sorting, it's going to be n squared log n. Okay, so I'm back to the algorithm at the stage where we built the maximum weighted spanning tree. And now I'm going to transform this resulting undirected tree into a directed tree. And magically, the way I'm going to do it, this is maybe the coolest step in this algorithm, I'm going to choose a root variable and direct everything away from it. Now I have a directed tree. Okay, it's clear? I have an undirected tree. I'm choose any vertex you like and make it a root and direct everything away from it. That's going to be my tree. And then now I have to decide which numbers to put on the edges. Because I see these two edges, x7 and an arrow from it to x9, I'm going to now compute the probability P of x9 given P of x7 from my data by counting. And I have a tree. And it turns out that this is the best probabilistic tree you can have, the best in the maximum likelihood sense on this data. Now, I just gave you an algorithm. It's a nice algorithm. What has to be shown to convince you that this is the right tree? First of all, there are three things. One is Okay, let's do it in this order. I have to show that putting the conditional probabilities on the edges is the right thing to do. Notice that I did not use any conditional probabilities during the algorithm. I used the ix of y, ixy. Nevertheless, at the end, I'm going to put this, and this is the right thing. 2, I have to show that using I of xi as a way to do this spanning tree, these were the weights that govern my spanning tree algorithm, is the right thing to do, rather than using p of x comma y or p of x given y or any other random number between x and y that you choose. This is the right thing to do. And this is directly related to the fact that I'm measuring distance between distributions using this KL divergence, which I defined before. And then 3 is that transforming the resulting undirected tree to the directed tree can be done this way, by just choosing any root variable I want, making it a directed tree. So I'm not going to prove anything. There are proofs for 1 and 2 in the notes. It's a little bit technical. It's outside the scope of what I want you to know, but if you do want to know, go and try to understand it. The 3 is actually cool and easy, so I want you to think about 3. Why is it okay to take an undirected tree and any way you choose a root and direct everything away from it? It turns out, and this will be a problem in your problem set, that any way you do it, you're going to get the same probability distribution. So I'm not going to prove this now. What I'm going to show is a quick example so that we'll understand what we're doing here. So you should be thankful. This is everything we're skipping. Okay, so the third bullet is transforming the resulting undirected tree to a directed tree. So you have to think about what does it mean that irrespective of which node I've chosen, I get the same probability distribution. You should be able to think about it, define it to yourself, and write it down. Okay, so this algorithm is a famous algorithm. It's called the Chow-Lu algorithm. It was actually developed in the 60s, like all the good things, by information theorists that actually developed it in the context of data compression. They had a lot of data, just like the data that we have here, and they want to represent it in a compact way, so they invented this notion of a probabilistic tree as a way to compress it. Later on, Judea Pearl, that invented and did most of the fundamental work on Bayes nets, or probabilistic representation in general, invented the algorithm again in the context of Bayes nets, and it was later on invented a couple more times, but basically it's the same algorithm. Example. So what I'm doing here is I'm giving you a quick example. I cheated a little bit, but I just to make sure that we understand what the algorithm is doing, and I'll tell you where I cheated here. So this is what the algorithm is doing. It's I have these 4 data points, 4 dimensions, sorry, 3 data points, the same 3 data points that we had before, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, and I'm running the algorithm. What do I do? First of all, I have these 4 variables, A, B, C, D, and I'm determining P of A, P of B, P of C, P of D. And hopefully you would agree that P of A being 1 is 2/3 here. P of D being 1 is also 2/3. Now I need to compute P of X, Y. So for each one of the values, and I have a lot of values. I have 16 values here, right? I think. I have to compute P of AB as 4 numbers. AB being 0, 0, 0, 1. Actually, I'm wrong. I have 24 numbers. Yes. 4 choose 2 is how much? Used to be 6, right? So 6 times 4, 24 numbers that I have to compute. So for AB, this is the probability of them being 0, 0, 0, 1, 1, 0, 1, 1. Same thing here. For C and D, this is the probability of CD being 0, 0, 0, 1, 1, 0, 1, 1. So these are all the numbers I have to compute. Now I have to compute P of AB divided by P of A, P of B, in order to compute the information gain, the I, X, comma, Y. So I'm computing this. Now I have to take log and a weighted average. This is where I cheated. I did it without logs, so that it will not be ugly. But the order of the points is still going to be the same. So notice that when I say here I of AB, it's not I of AB. It's an approximate computation without the logs because I didn't want to make it ugly. Now I have these numbers. Now I can generate a tree. So I'm running the spanning tree algorithm. So first of all, I put an edge AB. This is the largest number here, I think, among all these numbers. And then I put an edge from A to D. And then I put an edge from A to C. Now I have a tree. So that's the next step of the algorithm. I have an undirected tree. And now I have to choose a node. And this is going to be your exercise. Choose a node. I have 4 options. I can take B and direct everything away from it. If I do this, what are the conditional probabilities I have to compute if I chose B to be the root? Yeah, A given B, D given A, C given A. I could also choose A to be the root. And then the probabilities that I'll have to do is B given A, D given A, C given A. I could also choose D to be the root and ask you the same question. And the cool thing is that it's going to give me the same probability distribution. So that's something that you should be able to handle. Think about it and write it down. Okay, so basically we are done. We gave a learning algorithm for a probability distribution. To make our life easier, I gave you just the case of Bayesian trees, not general probability distribution. It's going to be harder for general probability distributions, but it's still good enough both in practice. It's often, if you can afford doing n-square numbers, is going to be better than naive Bayes, for example. And in general, it's a cool algorithm that allows you also to think about probability distribution, and understand kind of the Bayesian theory. We used all the tools that we could have for Bayesian, for Bayesnets or Bayesian stuff in general. Questions? Okay, so we're done with this. Next week, we're going to do clustering and dimensionality reduction, and that will be the end. Okay, thank you. Have a nice weekend. And as I said at the beginning, we're going to extend homework 4 to be due Monday midnight, I think. Sure.
It's very helpful.
Okay, good. I'm glad. Yeah.
Running into an interesting problem right now.
We
Tweaked the algorithm a couple times. I posted on Piazza about it.
what are the issues? It's computational issues or?
Accuracy related. So, I mean, I've tried implementing the algorithm in 3 different ways. all three ways are giving me different accuracies, but they all